Online lecture number 15. Last time we spoke about reactive intermediates. These reactive intermediates, they can be formed by heterolysis, where the electrons from a covalent bond, both electrons, they jump to one of the two atoms of this molecule, and that results in the formation of an anion B and a cation A. But reactive intermediates can also be radicals that form by homolysis. In this case, the electrons from the covalent bond, one of them jumps to B and one jumps to A, and that results in two atoms that each have unpaired electrons. So this is by homolysis, and heterolysis or homolysis, they have different curly arrow notations. So I introduced to you different reactive intermediates: carbocations, carbanions, and radicals. So for the carbocations, you have usually planar geometry. For the carbanions, you can have both pyramidal or planar geometry with different hybridization degrees. And for the radicals, you have planar configurations. So now, what determines the stability of these intermediates? So the stability is first determined by electronic effects, and second can also be determined by steric effects. We will talk mostly about electronic effects, so let's start with this. So if you have a reaction, you want to write a reaction equation, then you need to decide which arrows you draw, in which direction they go. And for this, it's very useful to understand which of the atoms in the reactants are electron withdrawing and which are electron donating, so that it helps you to identify the direction of your curly arrow and also to understand the stability of your intermediates, which gives you an understanding of the equilibrium of the reaction. So electronic effects can be classified as either inductive effects, hyperconjugation, or mesomeric effects. So in the following, we'll talk about these three different types of electronic effects, and we'll start with the inductive effects. So those inductive effects, they happen due to electronegativity differences of the atoms in the reactants. So here's a scale of different atoms and their corresponding electronegativities. So you see carbon and hydrogen, they have very low electronegativities, quite similar, but then sulfur, bromine, nitrogen, chlorine, oxygen, and fluor, that is in the direction of increasing electronegativity. So this, knowing which of the elements are more electronegative, helps you then to decide which atoms are electron withdrawing and which are electron donating. So now we split inductive effects into two types. The first type is when the inductive effect causes a polarization of the C-C bonds in a molecule by an electronegative heteroatom. So heteroatoms can be these, and anything that is more electronegative than carbon is now having a so-called negative inductive effect on a C-C bond, also known as -I effect, negative inductive effect. So the group that is more electronegative than the carbon is here generally X, and we call that group a -I group, and group with a negative inductive effect. So this group will be partially electronegative, or have a partial negative charge, causing the carbon to have a partial positive charge. And since the polarization here happens from this heteroatom, the direction of the polarization is from the left to the right here. So here's an example. As you see, chlorine has 3.16 electronegativity in comparison to carbon 2.55. So chlorine is more electron withdrawing. It has then a partial negative charge, and there is a direction of the polarization from the carbon to the chlorine. Oxygen is also more electronegative, even more than chlorine. So this causes also a partial positive charge on the carbon. But here is also a hydrogen attached to the chlorine that also gets electrons withdrawn, becoming partially positively charged. This inductive effect, for instance here for chlorine, is not only to the next carbon atom, but also to the one following and even afterwards, but it weakens over the distance. So we indicate this with these deltas. The more deltas you have, the lesser is the partial positive charge. So here's a very kind of complicated situation where the 2 electronegative oxygen, this one draws electrons from this carbon, but this carbon also gets electrons withdrawn from the other oxygen, so making this have 2 polarization directions, both towards the oxygen, those that are starting this polarization, and also the carbon in the back here has a slight positive partial charge. So in general, what can we learn with this negative inductive effect, this -I effect? It stabilizes reactive intermediates that are anionic, so carb anions, because the electron withdrawing or electronegative properties of these heteroatoms, they absorb basically this negative charge that the carb anion has, and stabilize it so that it doesn't quickly want to react with another molecule, because the electron is shared basically between these electronegative groups. So there's the second inductive effect where the CC bond polarization is caused by an electropositive heteroatom. So generally the electronegativity of carbon is already low, so there are only very few atoms or elements that have a lower electronegativity of carbon. So, and we call this a positive inductive effect, +I. So here is the general definition of it. This Z group is now a +I group. It has a lower electronegativity than the carbon. So the polarization is this time caused because from the partial positive charge, and the polarization direction goes from here to the partial negative charge. So example could be lithium. Lithium is slightly less electronegative than carbon, so the carbon is basically withdrawing the electron from the lithium, and this here should be a minus, not a plus. The carbon is now basically an electronegative. And here's right, negative partial charge, but now we have the heteroatom being a magnesium bound to a bromine also, but the lower electronegativity of the magnesium causes this to become partially positively charged. Again, polarization direction is from right to left. So the stability, these +I groups, they, unlike the -I groups, they stabilize. The -I groups stabilize carb anions. The +I groups stabilize carbocations. So here I have a ranking of the stability of a reactive intermediate, and now these +I groups are methyl groups or alkyl groups generally. When a carbon is positively charged, then it is more electron hungry than an uncharged carbon. So the uncharged carbon from these alkyl groups here, now they are less electronegative than the carbon itself, which is positively charged, and therefore the positively charged carbon draws the electron density from these alkyl groups towards itself. And now what's interesting to observe is the more alkyl groups the carbon is connected to, the carbocation, the more stable is this carbocation. You see, for instance, the least stable one is the one that has only hydrogens as functional groups for the carbon cation, while with increasing amount of alkyl groups you have more stability. So this cannot only be explained by inductive effects. Generally, as I said, alkyl groups are stronger in +I groups than hydrogen groups. And why is this? This is because of a stabilization mechanism called hyperconjugation. And this is what I explain next. So I told you before, a plus inductive effect is when we have a heteroatom here that is less electronegative than the carbon. So we have here the example of a carbocation reactive intermediate, and it withdraws electron density now from the methyl group. So this stabilizes the carbocation, but we've seen before hydrogens do not stabilize it as well as the methyl group. So this is because of hyperconjugation. So here I draw the same molecule, now also including the orbitals. So remember, the carbocation is planar here. It has an empty p orbital, and the methyl groups, it's sp3 hybridized, so it has here an sp3 orbital, there an sp3 orbital, and there, and here, so 4 sp3 orbitals. But what you notice here, I only draw one sp3 orbital, which is connected, of course, to an 1s orbital of a hydrogen, sharing this pair of electrons. And now this one sp3 orbital is oriented this upward direction, unlike these other two which are oriented downwards, and it has the same orientation in the 3D space than this empty p orbital. And because of that, you can have some overlap between the two of them. And this overlap is called hyperconjugation. Now, there's the plus inductive effect, right? It causes a polarization of this sigma bond. But there's also now this sp3 orbital that has this orientation that experiences this inductive effect from this empty p orbital, and it withdraws electron density not only here through the sigma bond, but also from this one sp3 orbital that's connected to this hydrogen. That is called hyperconjugation, and this is some kind of delocalization of the electrons. We'll see later, delocalization is something that is very important for the stabilization of reactive intermediates. So this delocalization of these electron pair from this sp3 orbital by the electron attracting empty p orbital, that's called hyperconjugation. So yeah, here's just written what I said. The delocalization of this electron between the p orbital and the sp3 orbital. So here now you have both hyperconjugation and a plus inductive effect, and they together in conjunction they stabilize this carbocation. So remember, for the hydrogen as a functional group, it doesn't have this sp3 orbital, so it doesn't provide this additional hyperconjugation. That's why methyl groups are better plus I groups than hydrogens. So it's the same thing. You don't have to have a carbocation, but you can also have a radical carbon where there's one electron missing, and it also is hungry for another electron from these surrounding methyl groups. And the methyl groups also stabilize this carbon radical by hyperconjugation and plus inductive effect. And the hydrogens, again, they are not as good as in hyperconjugation. So you have more stability of a reactive intermediate if you have both an inductive effect together with hyperconjugation. Yeah, that's it for this online lecture. And learning this, you now are able to solve the homework problem 19.2. Later!